Good morning, students. Today we are going to start the chapter of Mathematics 2, which is Higher Order Differential Equations. This talk is about Introduction to Differential Equations. Already, all of us know that in engineering, main problem-solving techniques contains differential equations. Today we are going to cover the first part of this differential equations. We are about to start a very particular type of differential equation, which is known as higher order differential equation. In that also, we are going to discuss a particular type of higher order differential equation, which is non-homogeneous or homogeneous differential equation with constant coefficients and which is linear by nature. We'll also see how to understand this differential equation in form of its solution. How to figure out what are the solutions of differential equations, and also how to identify the components of solutions, like what are the parts of solution. So let us start this first part of higher order differential equation. Now as you can see over here in definition, the general form of higher order differential equation, which is non-homogeneous and with constant coefficients, is given by this equation. Now you need to understand first of all that this y raised to n in superscript over here, it indicates the order of differentiation of y. Throughout this equation, we are assuming that y is dependent variable which is depending on one independent variable x. It simply means that this y raised to n in small brackets indicates nth order derivative of y with respect to x. The coefficient in multiplication over here is an. This an is a constant coefficient. The next term is an minus 1, and in multiplication we have pi raised to n minus 1. This means that this is function of x and it is multiplied by coefficient an minus 1. And if we continue the same up to so on, at last we will receive a0 into yx. This a0 is also constant and this y is a function y which is in the equation. So this is the left hand side of the equation. You can see it is a linear equation. Linear in the sense there are no non-linear parts in the equation. Now, why we can say it is a linear, and what are the non-linear components? Y raised to n, it is with power 1. So the order of this equation is n and the degree of this equation is 1. Order of any differential equation is identified by the highest order derivative appearing into the equation, whereas the degree of equation is the power of that highest order derivative. So over here y raised to n gives the order of equation and its power gives the degree. As degree is 1, it simply means that the equation is linear equation. One more thing we need to check, that there are no cross terms of x and y. So here you can see the term y is multiplied by constant coefficient, so there are no chances for non-linearity. Now coming to the right hand side, over here it indicates r of x. R of x is a random function of x. If this is non-zero, then it is known as non-homogeneous differential equation. But if this part Rx is zero, in that case, this whole differential equation is homogeneous differential equation. So combinedly, we can consider homogeneous as well as non-homogeneous differential equations, linear and with constant coefficients. Over here, a n minus 1 up to n, these are all the constants. Rx is a random non-zero function of x. This will give you the definition of non-homogeneous differential equation. Now, let us consider second part. How to figure out the solution of this differential equation. The solution of higher order differential equation with constant coefficient, linear by nature, homogeneous or non-homogeneous, is known as general solution. What do we mean by general solution? The general solution is divided into two parts, CF and EI. CF is the abbreviation of complementary function, which is in notation given by y subscript c of x, means it is a function of x which is denoted by yc of x. The second part is particular solution, which is yp of x. P indicates the particular solution, C indicates the complementary function. If we take addition of these two, it gives us the general solution for given differential equation. So the whole idea of solution of differential equation is to identify function y which satisfies the given differential equation. And as I told you in this talk, it is divided into two parts. In upcoming videos, we are going to deal with these two components, CF and PI, in detail. How to find CF and how to find PI. Combinedly, which will generate the solution of differential equation. Now, let us go for some examples. And let us consider a particular case. If we have a second order differential equation, this will be the ideal situation in our curriculum. It may happen that you get third order, fourth order, or any higher order differential equation. But to understand a theory part or to understand a technique to solve it, we'll always consider second order differential equation. So this is the form of second order differential equation. Y double dash plus C phi dash plus C2y equals to Rx. So what I did over here is I considered this constant coefficient equal to 1. So if there exists any constant coefficient at the highest order derivative of y, should take a denominator of all other constants. It won't make any difference in the equation, but this is considered to be a standard form. Now what I do, instead of writing always y dash, y double dash is a tedious process. What we are going to introduce is the differential operator. What we'll do, we'll take d raised to n as d raised to n upon dx raised to n. This differential operator is now denoted by capital D raised to n. Parallelly, you can say that 1 upon d, it indicates the first order integration. Now, if we consider this differential operator, let us see how this equation is going to change. So, this y double dash will be d square of y, this y dash will be d of y, and this y will remain as it is. Along with the constants, it will give you differential equation d square y plus c1 times dy plus c2 times y equals to Rx. You can take this y outside this equation on the left hand side. So what it gives you at last is the differential form in this way, f of dy equals to Rx. Now this f of d over here is a random combination of capital D and some constants multiplied by y and equal to Rx. This will be the first step in any solution technique of higher order differential equation. Now let us go for some particular examples. Suppose you have y double dash minus 3y dash minus 10y equals to sin x. What we can do, we can turn this equation to be d square minus 3d minus 10 of y equals to sin x. So this function over here, d square minus 3d minus 10, this is nothing but our f of t. Let us consider second case, y double dash plus 10y dash plus 21y equals to e raised to x. So here it is d square plus 10d plus 21 times y equals to e raised to x. Third equation, y double dash minus y equals to log x. So it will give you d square minus 1y equals to log x. Fourth equation, y triple dash plus 5y double dash minus 3y dash minus y equal to a polynomial x squared plus x plus 2. This will give you d cubed plus 5d square minus 3d minus 1 times y equal to x squared plus x plus 2. All these equations are non-homogeneous differential equations, as the right hand side of the equation is always non-zero. Sometimes it may happen that the right hand side of the equation is 0. In that case, it is known as homogeneous differential equation. Now here you can see the order of this equation is 2. Order of this equation is also 2. Over here order of this equation is 2. And here order of equation is 3. So these are some examples of higher order differential equations. In upcoming videos, we are going to see how to figure out solution for this type of differential equations. You should pause and ponder in between this video while revising and try to understand the structure of higher order differential equations with constant coefficient, linear by nature, homogeneous or non-homogeneous, and you should also take care of the parts of the solution, which is CF and PI, and also try to consider some differential equations and convert them into differential operator